OK, so start with the full theory current. I'm not going to distinguish too much between pieces that come from like charges, like the electroweak charge and stuff like that. That's not going to be our main focus here. We can keep track of all that. Our main focus is going to be understanding the QCD effects for the jets. So we've already done this. The current that has a psi bar psi gets matched in SCT onto something with two Wilson lines. There's a label. There's another label. And we can also make a field redefinition. And let me not put zeros on the field after the field redefinition, since that makes it notationally cumbersome. So this goes to this after making that field redefinition. OK, so this is something we talked about earlier. And the Wilson lines here are capturing diagrams. As I said earlier, where you could have, say, two n collinears and one n bar, and then this guy is off shell, so that goes into a Wilson line once you match it onto the, so if this is the full theory, once you match it onto the effective theory, you get various extra gluons coming out of your operator, which are coming from these Wilson lines, and it's because you're integrating out off-shell particles. So if you just look at the kinematics, then there's already actually some fairly powerful restrictions. We're in the center of mass frame. Momentum conservation says that if we think about all particles in the final state as either being n collinear, n bar collinear, or ultrasoft, then the initial momentum of the virtual photon, or virtual Z, has to add up to all the final state momenta. And if we just look at the large part of that in the center of mass frame, n bar dot q is just capital Q, and that's n bar dot pxn plus things that are small. And likewise, n dot q is capital Q. N dot px n bar, which is large, order 1, plus small. So these guys here are leading order in the power counting, and these guys are suppressed. And what that happens is, like in the example we talked about when we were doing beta S gamma, we have these labels, omega and omega bar, on our collinear fields up there. They just get fixed to the Q's by momentum conservation. So I said this was generically going to happen whenever we had operators that had only one type of building block in each collinear sector, and that's exactly the situation we have. So momentum conservation is strong enough to fix that omega is equal to Q, and so is omega bar. So the first thing I want to do is show you how to factorize the cross-section in this case. So what would you do in QCD for this cross-section? Well, you'd say the cross-section is a sum over some restricted set of final states which satisfy the kinematic criteria that I'm interested in. You'd have a momentum-conserving delta function, and you could write it as a sort of a leptonic or leptonic tensor, and then kind of a hadronic tensor, the same way we do for DIS. So you could start with that formula, which is really true for anything that you might want to measure. which is just imposed by kind of what states you include here. And I haven't yet specified exactly what I'm going to measure. We'll still have to put that in. So part of what SET does is make these restrictions into something that shows up in the operators rather than showing up in the states. And ideally, we'd like to sort of get rid of the states eventually and be able to see how to calculate things. So in SET, once we know that we're in a Dijet configuration, we can think of the state as having been composed of sort of pieces for the different sectors. And we know that this is an OK picture because our Lagrangian for these guys factored. And when the Lagrangian factors, that means the Hamiltonian factors and the Hilbert space factors. After the field redefinition. OK, so we can put in our expansion of the current at the top of the board over there, and then put it into this formula and see what we get. And there's some prefactors. I'm now summing over just these states. There's still some restrictions depending on what I'm measuring, but they're different restrictions and they're simpler. There's still momentum conserving delta function, but I can write it out as pxn, pxn bar, px ultrasoft. And because of the states factor, I can factor also, with a little bit of work, the operators. So I can write the operators. I'll just write it down. I think it's really clear. And I'll tell you some of the things you have to do to get there. So I am skipping some steps here because if we do it, we can do it very carefully and we can write out each step one at a time, but there's a lot of writing if one does that. So I'm kind of trying to write steps where I think it's intuitive what the results are and skip steps that at some level can be filled in either by looking at the literature or you just believe me. So we had these operators that were still tied together in some sense because there was a color contraction of an index between them. But we can get around that basically using some, once we realize that the matrix elements factor like this, we can use some color identities and put it in this form. So there's some overall prefactor, so 1 over NC, I didn't write. There's some overall prefactors, but the color is separate. There's a trace, if you like, over color here. And these guys here are traced into color singlets as well. Right trace in each case. So just using some color identities, we can do that. So remember, the fact that the states factor and that the operators can be written in a product means that all contractions are happening between these guys and these guys. That's why I can separate the matrix elements in the way I have. And the only thing is then that there could be color indices tying these guys together, but it turns out you could deal with that as well. When you deal with the color fields, you could get things like, you could get a TA in here or something. Well, you could get, for example, TA or something, but then there's some ways of getting rid of those terms related to the fact that this has to be, well, you have to argue that certain things are color singlets, but I'm not going to go through that. So there's terms that we're dropping here, and those are the other high order, those are the other power corrections. So this keeps all the power corrections of the first type, mu s, lambda QCD over mu s, because those can still be encoded in our soft function, which is going to be this thing involving the soft states. But it drops the other power corrections.
How do you know that since you provide the soft Wilson lines by looking at like perturbative diagrams?
No, I didn't. I can derive I don't need to look at perturbative diagrams to derive the Wilson lines. I just derive them from the SCT Lagrangian by making the field redefinition.
So you're saying that because the Lagrangian decoupled,
Yeah.
that's good for all
soft particles. Yeah. So far we actually haven't needed to use perturbation theory. And the idea here is that we're not going to use perturbation theory. We're going to write down some formula that's true to all orders in perturbation theory, and we're really only trading the power expansion. That's what we're focusing on here, without thinking about things as perturbative things. Although obviously some of these functions will be perturbative functions that we will end up wanting to compute. Okay, so let's think about what res prime means. And it's really a reminder that this formula is only really valid if we're making a measurement on the final state that really puts us in this configuration. So it's not enough to say we are in this situation. You really have to measure something that makes you in that Dijets configuration. And that's important to remember. And so we're going to measure the hemisphere invariant masses. So we need to cook that into our formula. And there's a very easy way of doing that. We say that the following is true. I can write 1, which is equal to an integral of 2 delta functions. So this formula is obviously true. And then what I'm going to do is instead of integrating this, I'm going to move it as a d sigma d these things. And that's going to leave these delta functions inside the formula here. But since they depend on collinear and soft momenta, which are the momenta that are in these states, they're going to be sort of tightly connected to the whole thing, whatever is going on in this formula. It's not like they commute with this xn. They only commute with the xn if I can make them into the identity by integrating over this. But once I pull this through and put it over on the right-hand side, left-hand side, then you have to leave these delta functions there. They're specifying the measurement. Okay? So this is like a total n collinear momentum. And this is like the total ultra soft in hemisphere A. That's what the A means. So I divided everything into hemisphere A and B. Obviously, all the n collinear particles which are going in that direction are in that hemisphere, but the soft ones could go in either case. And so then there's this soft momentum in hemisphere B and soft momentum in hemisphere A. Now, this is unexpanded. I can also expand these delta functions. And I only need to keep the leading order piece if we're working at leading order. And so the leading order pieces are as follows. There's an order lambda squared piece. This is lambda squared. There's an order lambda squared piece from the collinear momentum squared. And since this is a total collinear momentum, it can involve multiple massless particles. It doesn't have to be 0. And then there's a cross term between the softs and the collinears. It's also order lambda squared. This is order 1. And this is order lambda squared. And that term's the same size. And then all the other terms are higher order. These terms are suppressed. So this is really all I need to keep. There's also something else that effectively we've done by setting things up, and that is, in general, you could think that the collinear particles would have some perp momentum, but we aligned our axes with the jet axis, so there's actually no perp momentum there either. So that guy is really just, we can pull out a Pn minus, and then we have Pn plus. Plus KSA plus. And we also know that Pn minus is Q. That was fixed by kinematics. Okay, so this simplifies quite a bit. And we're going to drop all the power suppressed terms. All right, so that is one thing. So then I can do what I said in words, write this guy, and it will have these two deltas that are under the sum over x. They don't commute through with it, with that. They depend on x. Now, another thing we would like to do is to factorize the measurement. So this measurement here involves a sum of a plus momentum in linear and a plus momentum in soft. We'd like to, and it's all in one delta function. We'd like to write it as separate delta functions that we can associate with those different parts here. We'd like to have a separate thing here from these guys. And that's actually very easy to do. We simply write the following. Just introduce some more delta functions. So there's this tying together delta function. K plus is just some dummy variable. It's not the momentum of any state. It's just a dummy variable. Whereas Pn plus and KSA plus were momenta of particles in the state. So this guy can then associate with the, put them together with the n-collinear matrix element. Right, which is this guy here. Forget what color he was. And then for the ultra soft, we can associate this delta function. So that's what I mean by factoring the measurement, that we can put the piece that depended on the state together, and then you can see that we can move our, well, okay, we have to also factor this delta function. I should say that too. That's the part that I'm not going to go through. But we can play similar games, expanding and factoring this delta 4 as well. Besides just being a little bit tedious, it's not really any more difficult. Maybe a little more difficult. So we factor that guy too. And then there's one other trick that we want to do, which is useful. And that is that we can write some deltas in Fourier space. So we can always write a delta function as an integral over a phase. And that's convenient because in the phase, the momenta that are in the delta function also factor. So I can write it as a product of two separate factors like this. There's some halves, but it's conventional. Okay, so this guy here, which is the guy that is associated to the state, it looks like a translation operator, right? If you have an e to the I x dot p, that you can put into your matrix element, and you can translate the fields, which are in this formula all at 0. They're all at space-time 0. What you can do with this guy here is you can put it into the matrix element and translate the fields to point x. then you'd have like a chi nx minus. So that's how we can deal with that guy. And so if we do a bunch of stuff like that I'm not going to go through on the board for you, after some work we get something which is kind of an intermediate step of our factorization, which I'll write out. So you can get some idea of, if I jump to the final answer, it's kind of too simple to see what's going on. So let's write this one out. So I was focusing on the n-collinear matrix element, and everything I was writing, I wrote this delta function, but there's of course another one for the delta m bar, and I do the same thing for him. So we got k plus and l plus by factoring the measurement there. You get a k minus and an l minus by factoring the other measurement. One thing that comes into that makes this guy here a little more complicated is you have to think a little bit about residual and label momentum, but at the end of the day, the result is what I'm writing. So this is going to be completely factorized into 3 independent things. There's one set of collinear fields for the quark. And then there's another for the antiquark, if you like. You're specifying whether it's a quark or an antiquark by the label. So the fact that this label here is positive means that this is a quark, and maybe this should be a minus q. And then this guy is specifying the antiquark. And then there's the soft part. OK? So this is a fairly messy one-board expression. But this guy here is factored. We have the hard modes here, collinear mode, n-collinear here, and bar collinear there, and the ultrasoft modes here, which I've already dropping my ultrasoft. So this last guy, if you think about what this matrix element is, it's just some function. We sum over all x of this, so we sum over all the intermediate states. The only thing we're fixing are L plus and L minus. So when we sum over states, we actually integrate also the momentum of particles in the state. You can think of that like those are different states. You have to sum over them too, but it's a continuous label, and since therefore you integrate over the phase space. And that's what we mean when we write these sum over x's. That includes phase space integrals. And so this momentum gets integrated over, if you like. But then there's a component that gets fixed, which is the total momentum of plus or minus momentum in each hemisphere. So this is just some function. So that, keeping the color the same, is just some function of L plus and L minus. And it's called a soft function. And at this stage of the game, it's actually encoding two different momentum scales. The L plus and minus, as well as sort of lambda QCD, which I didn't write explicitly as an argument. And L plus and minus, well, we'll see later. But you can think of L plus and minus roughly as like encoding the scale that's m squared over q. This will become more clear in a minute. So again, we need to figure out what these guys here are. That's a little bit more work, but not too much. And they're both, of course, mirrors of each other, so really we just have to do one of them. And then, if you like, the other is just kind of a charge conjugation. So this guy here we're going to write in Fourier space. That's a convenient thing to do. Because what we know about the Feynman rules in Fourier space, when we thought about the Feynman rules in Fourier space, we knew that the collinear propagators would only depend on the small plus momentum. So the x coordinates here, the x coordinates of our fields, right, those corresponded to residual momenta. But when we do Feynman diagrams, there's only the plus momentum showing up. That's the multipole expansion. You can think about it from the Feynman graphs, but it's really a general property from the multipole expansion. So that means that some of these integrals here are just trivial and give me a delta function. So I'm getting delta functions in some directions because of the multipole expansion in this formula. Because I aligned the axis, there was no perpendicular momentum, so it's really just this r plus that we get, and this thing here is called the jet function. So this is the non-trivial function that can show up. We do the same thing. We do the same thing for the case with the sum over xn bar, and it gives us another jet function. And by charge conjugation, it's the same jet function. Okay, but in this case, it would be q of some r prime minus, some other momentum. And so what we then do is we take this formula, plug it back into here, do all the integrals, and at the end of the day, we can actually we have lots of delta functions and lots of integrals, and we can boil everything down to just two integrals left over. And that gives us our final result, which I'll write this way. Okay, so it boils down to just involving these jet functions and the soft function. And then there's something that's called the hard function, which is just our Wilson coefficient squared. So rather than writing Wilson coefficient squared all the time, we just call it another function h. Okay, so this is the factorization theorem. So you see in this case, the hard function was just a multiplicative factor, unlike DIS. And where things are talking to each other, again, things are talking to each other, but it's the soft modes, ultrasoft modes that are talking to the jets. And ultrasoft momenta can change the mass, and that's what the correct mass, this is the total mass. The correct mass for the jet function is the collinear mass, and that's this thing minus this thing. So if you wanted to guess this formula, this is how you'd do it. You'd say m squared, just from the kinematic relation, m squared had a collinear piece and a soft piece. The right thing to evaluate the jet function at would be just the collinear piece, so that's the difference. And then the soft function could depend on these momentum, and you're basically led to a formula like this one. But we can also just, with the field theory, go through and derive it, and that's what I've been convincing you of, even if I was skipping some steps. All right, so this is the Dijets factorization theorem for hemisphere invariant masses. And a lot of event shapes kind of go along the pattern that we've done here. If you think about what would be the difference if I pick some other observable besides these masses, pick some other thing that you could measure that would tell you that there's Dijets, we just swap out the measurement part, and that would lead to, just see where it leads us. A lot of the steps would be exactly the same steps. So we did it for one particular observable, but the steps are the same if you do others. If you're in this situation where you have Dijets, there's more than one way of measuring an event to ensure you have Dijets. There's something called Dijet event shapes. They go under the names of things like thrust, C parameter, heavy jet mass. All of these things actually have factorization theorems that you could derive in a similar way to what we're doing here.